Hi, we're in our 6th lesson in Chapter 1 today. We're going to be talking about families of functions and how to transform them. So this also will be a little bit of review and perhaps a little bit of extension of what you've learned in your Algebra 1 and Algebra 2 classes. I'd like to start with a definition. A family of graphs is a group of graphs that share common characteristics, or shapes is a good way to say it. They share common characteristics or shape. The parent graph is what I would call the basic model. It doesn't have all the options on it, just the base model. We're going to talk about 7 such families of functions. We'll describe these things in several ways. This one, a horizontal line, is called the constant function, and its equation is y equals some number. This one happens to be 0, and that's the parent graph of all the horizontal lines. This guy is called the identity function. It also is a line, but as you can see, it's slanting right through so that whatever x is, y is the same thing. The identity function, this is the father, or if you will, the parent of all slanted lines. This one happens to have the equation y equals x, but we know that we can transform that, and that's part of what we're going to talk about today, by changing the rate at which it climbs or drops, and also how far up or down the y-axis it goes. So the parent model is called the identity function. It's the line y equals x. This one is the absolute value function, and its equation for the one that's shown is y is equal to the absolute value of x. The fourth of our families is called the parabola. And the equation for this particular parabola, the basic model, y equals x squared. And you know, that also can be transformed. And it's not just squares. This is the basic shape for anything that has an even exponent. So we'll talk a little bit about that further in this class. This function, which looks like, suspiciously like, half of this, is indeed that. This is the square root function. And if this guy was y equals x squared, this guy is y equals the square root of x. And you'll recall that the symbol means that we're only showing the positive side of the square root of x. Really, that's needed to allow us to call this a function. If we included both the positive and negative square roots, we would have something that doesn't pass the vertical line test, so it wouldn't be able to be called a function. This next one, our 6th, is called the cubic function. This particular parent equation, y equals x cubed, can also be transformed by moving it up and down, widening it out, changing the power. So if we had an odd power, we'll still get that ribbon type shape, but either narrower or wider, and we'll talk about that as we go on. And then this guy, the last of our families, is the cube root function. You can see that this one is the inverse of the cubic. In fact, it is the cube root of x. All right, there are our basic 7 models, and let's see what we're going to how we're going to talk about transforming them today. We're going to begin first by talking about reflections. So really there are 3 types of transformations that we can talk about. Reflections or flips, that would be kind of the slang name for this transformation. And so what I've done is shown the parent function here along with a reflection of it. And what I've done is shown you, so the red is the reflection image. When we change the equation to y equals the opposite of x squared, you'll notice that we get that reflection right over, which axis is that? The x-axis. This rule looks very similar to this. The only difference is, instead of, this one says do the opposite of x squared, this one says take the opposite of x and square it. And you'll notice that the blue and red, they've merged up here. when we do this kind of thing, that is when we do the function to the opposite of x, we get a reflection for sure, but not over the x-axis, over the y. And you can bear that out here as you look at the cube root function. This one has the rather unique thing that either the opposite of the cubic function or cubing the opposite of x, they look the same. One takes this graph and flips it over the x-axis, that would be this guy. The other takes the blue graph and flips it over the y-axis, which would be this guy. They appear the same. And then we did the same thing with the identity function, the line function. So y equals negative x is this guy. That's do the opposite. So do the function is y equals x, do the opposite of that, or it's the same thing as if you say y is equal to the opposite of x. So kind of interesting. And just to sum up what those rules say, if we do a rule that looks like this, y equals the opposite of f of x, okay? We change the sign of the entire function, if you will. That is a reflection over the x-axis. If we do the function to the opposite of x, that reflects it over the y-axis. And I think that that language that I used is kind of important here, reflection over y-axis. So I want to just go back and make a note about this. Our top rule here says do the opposite of the function. The bottom one, on the other hand, says do the function to the opposite of x, and you get very different results. Do the function to the opposite of x. All right, so our reflections, really they come about by changing the sign of either the entire function or by the sign of the input to the function. The next group of transformations we're going to talk about are translations, and those are moves up and down or left and right, and of course we could have combinations of those things as well. I've shown again the similar thing. Parent functions are in blue here, and the transformed function, transformed by this rule, you can see that that parabola, the basic shape, instead of crossing through at the origin, crosses through 3 units below. And that happened when we subtracted a constant from the function part of it. Here we've added 2 to the absolute value function, and it's the same deal, folks. We got that same v going. Everything's sloping or increasing or decreasing at the same rate. It's just that we moved it up 2 units on the y-axis by adding that constant. So this moves the entire function up c units. This moves the entire function down c units. And we've got the up and down accounted for. Now we got to think about left to right. And so I want to point you up here to these 2 pictures. Here's our cube root function. And see the change in the rule. Oh, by the way, use the exponent notation because that's easier when you're writing the equation than trying to get a radical symbol into it. X cubed would give us the blue thing, or the cube root, I'm sorry, cube root of x would give us the blue function there, but when we change it to give us the cube root of x minus 2, notice that that minus here actually shifted the focal point, the turn point in this function, 2 units to the right. That was with a minus, and that seems to be the backward of what you would expect. So we're going to just remind you that when you see that subtraction or addition inside the parenthesis, the actual move is in the opposite direction. Here we're talking about taking the cube root function and moving it to, it says plus 2, but what happens is that focal point again, that center point, that moves 2 to the left. So these guys go the opposite of what you would expect. It moves the entire function left c units here. And when we show x minus, that means we're moving to the right. Moves right c units. All right, so we've talked about reflections and translations. Yeah, dilations are the next that we'll talk about. And you can see that these dilation rules all involve multiplying by a constant. Translations involved adding and subtracting by a constant. Reflections involved sign change. These guys say if we multiply, we get different reactions. And you can see from the pictures that we get either wider, like this one got wide, or skinnier, like this one drew it right back into itself. Notice again that these are all accomplished by multiplication, but the multiplication is of different absolute values. Here it's the number 3, here it's the number 0.25, and it's also whether we multiply the function by 3 or whether we use as input to the function 3 times x. Okay? They give different reactions. So we've got some rules here, and we've got, what I'd like to have you do is I kind of have these mixed up a little bit in order. So I'm going to ask you to number these graphs 1 through 4, and as we look at the equations and write descriptions of what they do, we'll match what we get here in rule with either graph 1, 2, 3, or 4. So I'm looking at this one. This says y is equal to a constant bigger than 1 times the function. A constant, well, that's just a number, bigger than 1. So I'm thinking that that's this one. This first rule applies to that graph. Okay? And if you look at the change from the parent, when we multiplied by that larger number, multiplied the function by 3, we actually drew it in towards the y-axis. This one is called a vertical expansion. Vertical expansion. And you could think about the change that happens is this one becomes more vertical or closer to the y-axis. More vertical, dot, 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 closer to the y-axis. All right. The next rule is multiplying the entire function by a constant when that constant is between 0 and 1. So as you look at the 3 remaining graphs, the one that shows that the multiplier outside of the function rule and it's less than 1 but bigger than 0, that's this guy. Graph 3 goes with this rule. This one also, if we're going to talk about it in terms of being vertical, this one, though, is not a vertical expansion. It doesn't get more vertical. It gets less vertical. That is, it kind of spreads out farther away from the y-axis. They say vertical reduction, so we'll go with that. A vertical reduction. Whoops, I forgot the C. Vertical reduction. You could think about this as being less vertical or farther from the y-axis. Right? Y-axis has to do with verticalness, so farther from the y. All right. The remaining 2 rules, you'll see that the multiplier is now inside the parenthesis. That is, the function, the input to the function is being multiplied. Not the entire function, the input to the function. And we've got the case where the multiplier is bigger than 1, and again, the case where the multiplier is between 0 and 1. As you look at this one, where the multiplier is bigger than 1, it has to be this guy. So that's graph 2 goes with this rule. And again, what you're seeing here is that this graph appears to shrink. All right, it gets really close into the y-axis. However, this one is called a horizontal. So this one, we're going to think about it in terms of what it does with the x-axis. This is a horizontal reduction. That is, this thing, the new graph, the red graph, is less horizontal, or it's moving away from, farther from the x-axis. Okay. You can see too that which one do you think is growing faster? This guy, graph 1, this guy, graph 2. You kind of got to go with this one. This gets way high really fast, right? We're cubing, right? We're doing the function to the entire, to 3 times the input value. And it grows at a, so the cube goes with the 3 as well, with the x is a way to think of it. It grows very fast there. Our last graph, this graph 4, is called a horizontal expansion. Horizontal expansion. And as you look at this graph, you can see why you would call it that, because it's getting more horizontal. That is, it's flattening out right there at the center. So more horizontal here, closer to the x-axis. And that happened when the multiplier was inside the function rule and its value, its absolute value, was between 0 and 1. This one gets closer to the x-axis. Now, I know that you've looked at these rules before. I'm not sure that in your algebra classes you would have gone to this amount of detail to saying, okay, well, this is happening outside of the function rule. That makes it a vertical change. So that may be a little new to you, but the idea of multiplying by a number greater than 1, we're used to that making these functions get skinnier, if you will, or narrower is a way to say it as well. We're used to having, when it's a multiplier between 0 and 1, we knew that that made it fat. Now we're just being a little bit more explicit. Which direction is that fatness happening? So let's go on and see what we've got here. Some applications. The first activity for us, it says describe how the graph of a function that is 2 times the quantity x plus 1 squared minus 3, how that would be different from the parent graph. And the thing to do is think, what all has been done to this? There are 3 things we got to worry about. We've got a multiplier outside. We've got an addition inside the function rule, if you will. And we've got a constant here that's going to change things. So 3 things that we'd have to say. And it's, of course, it doesn't matter the order that we talk about them. But this 2 on the outside, this one is going to cause us a vertical. Remember, I'm looking right back on the last page, or thinking back to the last page. This is a multiplier of the function part of this thing, and it's outside. That's a vertical expansion because that number is larger than 1. That means it gets expansion. It gets skinny fast. When we have the addition inside the parenthesis there, we can say that the focal point, the turn point of this function, has moved left 1 unit. And the constant minus 3 tells us that that focal point, or the entire function, has moved down 3 units on the y-axis. So if we were to grab our graphing calculator and compare the 2 of these, all right, I've got my calculator with a graph screen set up. Let me enter a function in here. We want f of x equal to, and it's 2 times the quantity, x plus 1 squared, x plus 1 all squared, and then down 3. So if our prediction is correct, at the same time, you know, I'm going to go ahead and hit enter. I'm going to call up another graph, so that's in my menu key here. And I just want to take a look at the parent function, which would be y equals x squared. All right, the parent is red. Our rule is blue. And what I thought would happen, let's see if I was right, I hope it was. Vertical expansion, that means that it gets skinnier faster, and you can see that that's happening. If you look even, well, here, the distance between x's is a bit more than 2, and the difference in y's here is much skinnier. If we look at a difference of x of 2 here, fatter. So we are skinnier. Left to the 1, or left 1, yep, I see that right there, and then down 3, that focal point is moved left 1, down 3, or we move the vertex of that parabola. Very good. So our prediction was right on, And now we're going to ask you to graph this thing by hand because that's going to be a large part of what we ask you to do in the classroom tomorrow. One of the things that I've said before that I think is really true is knowing where important things happen in the graph, and that's what this lesson will help you to do. We've said that the vertex of this parabola is going to be left 1 and down 3. So what we got to think about is an x of -1. Instead of going through x of 0, this one has an x of -1. That's going to be an important spot. We already know what the y will be there, however we'll figure it out here too. If x is -1, then that parenthesis is 0, which makes this whole part 0. So y of -3. And to get a good picture of where this graph is at, we need to have 2 points on either side. So we want to have two numbers less than. We can go -3, -2. You certainly don't have to pick them so that they're right in a line, but it helps. That's a pattern, a helpful pattern for me anyway. And so now I want to figure out y values for each of these. If x is -3, -3 plus 1 is -2. -2 squared is 4. 4 times 2 is 8. And 8 minus 3 is 5. -3, 5. If we put -2 in as our input, -2 plus 1 is -1. -1 squared is 1. 2 ones are 2. And 2 minus 3 is -1. Now I know that parabolas have that symmetry thing going, so I know what these y's should be, but I'm going to check them just in case, just to make sure I didn't do some math wrong. If I make x 0, the parenthesis becomes 0 plus 1, 1. 2 times 1 is 2, and 2 minus 3 is -1. So yep, that symmetry is working out for us here. If we put 1 in for x, 1 plus 1 is 2, 2 squared is 4, 4 times 2 is 8, and 8 minus 3, 5. There's that symmetry. And let's go ahead and plot this graph. The vertex was at -1, -3. So there's his corner. At -2, this graph is going through the y of -1. At -3, it's all the way up in positive territory. So 3 and 5. And then again, the symmetry takes over. 0 and -1. So right here. 1 and 5. Right here. There we go, sketch that in, and there's our parabola. Not perfect, but mine never are. Good, that's the end of our lesson for today, all about families of functions and how to transform them. We want to encourage you to do the U-try for this lesson, please, and we'll get that in as soon as we can. Have a good evening.